Namaskar. Welcome to this channel Chemistry Made Easy by Dr.ARM. We are discussing the molecular orbital theory. In this topic, we are considering here today photoelectron spectroscopy. So this photoelectron spectroscopy is the additional part which explains about ionization energy. Well, last time we have seen the information or the discussion regarding the bond distances and energies. The specific energy or specific information about the energy of electron or orbitals, that is molecular orbitals, is obtained by using this photoelectron spectroscopy. Means you can see this photoelectron spectra. So this is the photoelectron spectrum and MO energy diagram or levels for N2. This is the photoelectron spectrum and molecular orbital energy level for O2. So here you will find these are the molecular orbitals. These are the names of the molecular orbitals. And this is the photoelectron spectrum of nitrogen. This is similarly the photoelectron spectrum of oxygen molecule, and these are the molecular orbitals involved in this spectrum. So we can get this important additional information about the molecules, that is regarding the ionization energy. So if we see the effect of, means when certain molecule is interacting with a photon of desired energy, it is capable to remove the outermost electron. So we can show this using the equation. Say this is the oxygen molecule. So when it is interacted or it is say irradiated with photon of suitable energy, it gives us the O2 minus, that is molecular ion plus one electron is removed. Here this photon has certain energy, and when this photon strikes this oxygen molecule or any molecule, it removes the valence electrons or outermost electrons present in the molecules. So depending upon the amount of energy associated with that photon, it can show the impact on the removal of electrons. Generally there are UV, the photons are UV energy, UV light, or we can have X-rays. So here you will find that when the photon or there is UV radiations are used, they are capable to remove the outermost electron from the molecule. And this is because, say if you see these molecules, and if this nitrogen has here these all electrons filled here, so there are, you can show here, there are electrons like this. So nitrogen has electronic structure like this, in the MOs are filled like this. So you will find that the last electron is present here in this sigma G2p. So UV is capable to remove these electrons from outer electrons. But X-rays are more powerful than UV radiations. So they are capable to remove the inner electrons also. Means they can easily remove the outermost electron as well as they can remove the inner electrons also. So this is because the X-rays are much more powerful. So by such interaction of photon with oxygen, we can get the oxygen ion, oxygen molecular ion. And here we know that when the photon strikes with the molecule like oxygen, it removes the electron, and that electron is also associated with some energy, and that energy is called kinetic energy of this electron. So from this we can find out the energy of this and energy of this electron. So energy of this electron can be obtained, and now from this we can get the ionization energy of the electron or that energy level. For example, if we are considering this energy level of this sigma G2p or electron present in it, then we can get this energy of photon minus energy of this kinetic energy, you can see kinetic energy of electron, this electron. So that will give us ionization energy of that particular electron or orbital. So here the ionization energy will help us to understand the binding energy of the electron. So now we can see what is the structure of this photoelectron spectrum and MO diagram, MO molecular orbital areas. So you will find here the photoelectron spectrum of nitrogen. So we have arranged this spectrum using the energy. So energy is increasing in this direction. So lower energy values are at top of this diagram. So this peak is at less than 16 electron volt of energy. So as we move down in this spectrum, the peaks are ending here up at energy level less than 18 electron volt. So as we move from this along this axis, we can find that we are using here the values from say approximately 16 to 18 electron volts, and you will find that we are getting this sharp peak, very long peak at energy level so much less than 16 electron volt, and this corresponds to the sigma G2p. Now you will observe here the fine spectral lines in this spectrum at about 17 electron volt. So these are corresponding to this pi u2p xy 2px and 2py molecular orbitals of bonding nature. So these are bonding molecular orbital. This is antibonding sigma u star 2s molecular orbital. So if we find this difference between these levels, first and third, it is about 3 electron volts. Now we will have this peak arising because of this sigma u star 2s. So from this diagram we can understand that the electrons present in this level require less energy to remove the electron using this photon. So if we strike this N2 molecule with photon, then it will require less energy. So you can find here the value. It is less than 16 electron volts. So if we go to this pi u molecular orbitals, the energy required is about 17 electron volts. Means it is greater than the energy required to remove this electron. And further, it is also important to understand that all these electrons are required, or molecular orbitals are required for bonding or strengthening the bond or showing the bonding effect. So you will find that the bonding is more, the bond strength or bond formation or bond is more contributed, bonding effect, or we can say bond is more contributed by these pi electrons rather than these sigma electrons. So these are also contributing, but the contribution is relatively less. But it is more contributed, means bonding is more contributed in nitrogen because of these pi electrons. Similarly, you will find that in this photoelectron spectrum, the values of energies are plotted here from 12 to 21 light years, and we are having peaks of energies, peaks of this electron spectrum appearing between 12 to 13. So you will have 4 such peaks. So these are corresponding to these pi g star 2p orbitals. Then you will get here fine spectrum, which is corresponding to pi u 2p. So this is bonding molecular orbital, this is anti-bonding molecular orbital. Again we will get this sigma g 2p orbital corresponding to these peaks. So these peaks are arising or appearing between 18 to 19 electron volts, and this last peak appears between 20 to 21 electron volts. So this is corresponding to sigma u star 2s. This is corresponding to sigma g 2p, and this fine spectrum is corresponding to pi u 2p. Now if we compare the distance between these first and third peak, corresponding to energy is 3 electron volts, and here it is 6 electron volts between the sigma g and pi g star 2p. So this will help us to understand that what is the correlation between the photoelectron spectrum and these MO diagrams. So these MO diagrams, MO energy levels will show the specific or whatever information that is we are shown in the previous lectures regarding the MO diagram for N2 and MO diagram for O2. In the MO diagram for N2, you have observed that the sigma u star is lower energy than the higher energy levels are pi u orbitals, and sigma g bonding molecular orbital is above this pi u. So here you will observe the order of molecular orbitals in molecular diagram, MO diagram. Here sigma g from 2pz is appearing above or at highest energy level, and pi u is lower energy. In case of oxygen, you will find that the pi u molecular orbitals of bonding nature are appearing above sigma g 2p. It means the order which is observed here is reversed here. The order of molecular orbitals which is observed in nitrogen is reversed here. So sigma g becomes lower energy and pi u becomes higher energy. There is small difference in these energy levels. So the reason or this experimental evidence in support of this MO order, molecular orbital energy levels, the order is supported by this electron spectrum of these electrons. Now we can explain these diagrams also. The photoelectron spectrum for nitrogen shows that we have shown here. So the nitrogen photoelectron spectrum shows the sigma g is higher energy than pi u. Now you will see that this is higher energy level, and therefore it is the electron present in these molecular orbitals requires less energy to remove the outermost electron. Means ionization energy of these electrons present in this sigma g are less, whereas ionization energies of these molecular orbital electrons are relatively more. But in case of oxygen, you will find that the pi u molecular orbitals are having relatively less energy. And if the electrons are also there in this, if the electrons are there here you will find in oxygen, the electrons of this pi star are having least energy, ionization energy. These electrons can be very easily removed. So it is given here that the ionization energy of these electrons will be about 12 to 13 electron volts. Now, in case of this pi u, the ionization energy of the electrons in these molecular orbitals are relatively more. So again, as we move down in this molecular orbital diagram, the ionization energy will go on increasing. So the peaks are also obtained here in case of other molecules like carbon monoxide. So carbon monoxide molecule have also same type of pattern of the photoelectron spectrum. So here another important thing here it is to understand is that these are the various peaks you are observing here, and if we consider only electron spectrum, it should give us a single spectral line, but you will find that the spectral line can be like this because it is highest energy and low energy peak. Now you will find here the fine spectral lines. So this is because the electronic spectrum, electronic transitions we see, means electron is moving from this electronic energy level to higher energy level, or it is removed completely out of that molecule. Then this transition takes place through vibrational energy levels. Now we can show here the electronic transitions. So this is, so if you see these energy levels, so these are the electronic energy levels. So this is, say, E1, electronic transition E1, electronic energy level E1 and E2, and you will find there are various such vibrational energy levels like V0, V1, V2, V3, etc. V0, V1, V2, V3, etc. So when electron is moving from one electronic energy level to another electronic energy level, it shows, it involves, means E1 to E2 transition involves the various vibrational transitions also. So every electronic transition involves vibrational transitions. Here you will find that there are various vibrational levels also. Means when electron moves from this electronic energy level to this second electronic energy level, there is involvement of vibrational levels, and because of this we find here the fine spectral lines. The spectral lines means instead of giving a single peak, there is a bunch of such fine spectral lines, and this is because of the vibrational transitions involved during the electronic transition also. The oxygen spectral line or the oxygen vibrational spectrum also shows the fine lines, and as we have seen before that the involvement of the molecular orbitals in bonding here is because of pi u. So pi u molecular orbitals both in nitrogen and oxygen shows more involvement in the bonding. So bonding is more strengthened by these pi molecular orbitals. So with this we will stop our discussion and see the next point in the next lecture. So please subscribe to this channel and press bell icon and like button. Thank you very much for watching this channel.